So, only 2 sections left on about the better root finding methods. So, just so you know, I will be doing a MATLAB diary today. So I'll have a number of examples carried out there. All right. So what we have is I'm going to show you a method for finding a solution of a nonlinear equation. Where the idea is really incredibly simple, and it's not often to see a simple idea, such a simple idea, really also be something so powerful and helpful for so many problems. But that's what we have here: fixed point iteration, also known as successive substitution. The idea is this, and the story of this chapter is we're trying to solve this equation, f of x is equal to 0. But what we can do is, if we were to algebraically rewrite this equation to be in this form, x equals g of x. Now, there are a zillion different ways we can do this. The simplest one is we define g of x this way. G of x is x itself minus some function phi of x times f of x, a function we want to find root of. And if phi of x is non-zero, then what we have is x is equal to g of x is satisfied if and only if f of x equals 0 is satisfied. So then the two equations, f of x equals 0, x equals g of x, really are equivalent. Okay, so then we have this very short algorithm for solving x equals g of x. So we choose some initial guess, x 0, and then we'll have k, variable k, serve as our iteration count. And all we're going to do is we just keep taking xk, substitute it into our function g of x, and then the result we'll call xk plus 1, and then we'll just keep going. We'll just keep repeatedly substituting our new value into g to get our next value, and so on. So x1 is g of x0, x2 is g of x1, and so on. That's it, until the iteration converges. If it converges, and that's for rho. We can't be certain that this iteration will converge, but I will be able to show you some guidelines on how to transform the equation f of x equals 0 into x equals g of x to try to ensure convergence. So if it does converge, then there's a sequence xk, so it has a limit. We call that limit x star, which I've been using this notation to refer to a solution of this equation anyway. And just to put up terminology, so x star is called a fixed point of g, also known as a stationary point, because the idea is you take a fixed point, you plug it into g, and you get the same value out. So so this algorithm that hopefully produces a fixed point of g is called fixed point iteration. So what we're going to do today is we're going to try fixed point iteration out on some examples, and also establish some theory about when it works, and if so, how well does it work. But yeah, this algorithm doesn't get much simpler than this. By the way, it's possible that you may have seen fixed point iteration before. It just might not have been labeled by that name. In a first course on differential equations, one topic, depending on your instructor, that might be brought up is the existence uniqueness theorem for solving about the solution of a first order differential equation. And so the proof of that theorem involves what are called Picard iterates. That is based on solving a differential equation using fixed point iteration. So the theory I'm going to show you here about fixed point iteration in general is used for that proof. But I remember when I taught DE, so in Math 285, when I would show that proof, the students would not be happy about it. They'd find it pretty painful. But okay. So here's some questions that come up when we rewrite the equation f of x equals 0 in the form x equals g of x. Does the function g even have a fixed point? Is there a way to guarantee that a solution exists? If a solution exists, is it unique? If there is a unique solution, will fixed point iteration converge to it? And also, if convergence does happen, then how rapidly does it converge? Because we've already seen one root finding method, bisection, that's rather slow. Can we do better this time? And I'll be able to provide answers for all of these today. Okay, so I'm going to start with an example. So we're trying to find the root of a function f of x is x minus cosine x. So if I want this to be equal to 0, of course, the most straightforward way to rewrite this equation in the form x equals g of x is just to do this, like x equals cosine x. So g of x in this case is cosine x. So what I'm going to do is I'm just going to arbitrarily choose the initial guess, x not equal to 1/2. Now, it makes sense to choose initial guess between 0 or between -1 and 1 because cosine can only give values between -1 and 1. So we already know in this case that our choice for g of x, cosine x, is bounded. So we should choose initial guess that satisfies those bounds. Okay. So now I'm going to flip over to MATLAB and try this out.
Another diary.
Oh, good. Two classes instead of one, so why not? Okay.
Another diary.
Yep, it happens. Okay, so I'm going to do fixed point iteration to solve x equals cosine x. And my initial guess will be 1/2. Okay. So I'm going to, for convenience, define a function handle. So I get declare variable g, or define a variable g to refer to by g of x. So that would be, so I use @ sign and then x in parentheses. That indicates that what I'm about to define will be a function of x. And then I'll put my formula, which in this case is just going to be cosine x. Now, I didn't really need to do this for a function as simple as cosine, but if a function you have in here is more complicated, then this is definitely something that you want to do. Okay, so this is function handle for g of x equals cosine x. And then I define my initial guess. I'll just call it x is 1/2. So now, what now that I have my g and I have my initial guess, all I'm going to do is run this one command several times. X equals g of x, and I'm going to make it print out my new x. So that's all I'm going to do is I'm going to take by 1/2, plug it in a G, get a new X, and again and again. And let's watch the numbers. Do we see some sign of convergence? So bit of a change there. Well, that's square root of 2. Wait, actually, I'm not sure about that. No, it's totally not. What was I thinking? Okay. Oh, sorry, yeah, square root of 2 is 0.866 something. Then if I keep going, so this would, in notation in the notes, this would be like x superscript 1. And then I take this and plug it into G. So I'm continually overriding x with the value I get from G of x. Okay, so unfortunately, it's jumping around a little bit.
Jumping around?
Yeah, it goes from 0.5 to 0.877 to 0.639, and now 0.802. So there's some oscillation.
So this is random?
It's not random because I'm just plugging into cosine. It has a random appearance because there's like a bit of an oscillation going here. But if I keep going, again, I want to do this like several times. That the values are starting to get closer together. They're still not all that close, but they're definitely closer together than they were. Notice we have 0.75, 0.73, 0.74, 0.73. And so we are narrowing in on something.
You get
Well, I got
0.6948 or something.
I got that up here, but keep going. Keep using that same command. So because notice,
I'm trying.
well, just keep using your upper.
7.524 0.3 0.7.
Keep going. Okay. All right. Yeah.
Did I get it?
Okay. Yeah. Okay. So you're right around here. Okay. Yeah. So notice that the values are starting to converge now, and this is going to take a while. So now notice the first decimal place, 2 decimal places are fixed. We're like 0.739-ish. Okay.
Mine's on 7403.
Keep going.
Seven threes, 9.
Oh yeah. I got that one earlier. So, okay. All right. So notice now the first 3 decimal places appear to be staying the same, and so now we are seeing for sure convergence. And if I keep going, it's just a matter of time before you'll see, even in format long, no decimal places changing.
That's the end of it.
And I'm still going. Keep using your up arrow. Okay. So now we have like the first 5 decimal places. So it is converging, but it's rather slow. I've done this.
Mine's on format short.
Yeah, so yours looks already converged, but if you do format long, you'll see it's still going. And I don't even want to count how many iterations I've done here. It's a lot.
I'm starting to get tired of it.
That makes 2 of us. Okay, so, but yeah, we see that now we're like, we have like 9 or so decimal places fixed, and I'm just doing rapid fire here. And eventually, yeah, looks like we have like 11 or 12 decimal places. Okay.
Mine's stopping at 0.7391.
Yeah, so notice the Johnson effect form only changing the last decimal place. Now, I mentioned earlier, bisection is a slowly convergent method, and this was too. So fixed point iteration is not inspiring a lot of confidence right now, but we're getting started. Okay, so very slowly, because later on today, tonight, we're going to find out why we're so slow. Okay. All right. Now let's look at another example. Big point. So here's a function f of x. So we're going to find roots of x squared minus 3x plus 3/16. Now, so this function, it has two roots, it's quadratic, so the roots have to be at 1/4 and 3/4. Now, if I write this equation in the form x equals g of x, then I'm just going to move x to the other side. So now my equation is x equals x squared plus 3/16. So that would have two fixed points, 1/4 and 3/4. So you can see if I plug in 1/4 or 3/4 into the right side, then I'm going to get the same value of x on the left side. So now I'm going to do the same thing. I'm going to define g of x to be this function on the right side, x squared plus 3/16. I'll go ahead and set my initial guess to be equal to 1/2. And let's see what happens. Now we'll do fixed point iteration for x equals g of x, which is x squared plus 3/16. So I'm going to define my g like I did before. Okay. So g is equal to x squared plus 3/16. And I'll define my initial guess to be 1/2. And let's see what happens. So we know that there are two solutions, 1/4 and 3/4. Which one are we going to get?
So converges very slowly.
That's what the previous example did. Let's see what happens with this one. So once again, I will do x equals g of x. So as I do repeatedly, x equals g of x.
Repeatedly.
Yes. Until we see convergence. We start at 1/2, and the values are definitely getting smaller. There's no oscillation here. It's just heading straight for the smaller of the two solutions. It would be 1/4. Okay. And you see after just a few iterations that that's where it's going. Still not all that fast. Okay. So, and look at my diary here. So if I
I think I've reached my convergence. Kind of.
yeah, so this will converge to 1/4. And there's no need to go further than that. Okay. Now that initial guess was halfway between the two known solutions, 1/4 and 3/4. Let's pick something that's definitely closer to the 3/4. I'm going to set x equal to 0.7. That's my new initial guess, closer to 3/4. Okay, so now I'll do the same thing. X equals g of x. It's still getting smaller. You think that because I'm choosing something that's pretty close to 3/4, that it would converge to that.
X equals what? So x equals
My new initial guess is 0.7. and then I do x equals g of x repeatedly.
So if we use this as a format.
Definitely.
X equals G.
Yeah. So it's not going to converge to 3/4. If I keep going, eventually I'll just end up at 0.25 again. So still converges to 1/4, even though closer to 3/4. All right. Now, okay. So one other possibility is, okay.
Even though it's closer.
Yeah, my initial guess is closer to 3/4, but this will still converge to 1/4. So now I'm going to choose yet another initial guess. What if I choose something greater than 3/4? So x equals 1. And now I do x equals g of x again. Well, now it will start growing, which is not a good sign.
Not a good sign.
Yeah, but so apparently it's impossible to get fixed point iteration for this example to converge to 3/4, no matter how I choose the initial guess. In fact, I haven't done it here, but if I were to do it, if I choose initial guess that'd be like 0.74999, something like that. It still won't converge to 3/4.
Can't get 3/4 with this guess.
Yeah. So
So now we're.
so we can, why would that be? Okay. Not losing my place in my diary. Okay. All right, so that's all I'll do for that example. But we'll come back to it later. And that's why I will be able to tell you in time. So now let's look back to the notes. But I will return to the diary later.
My comment in the diary was can't get 3/4 with this guess.
Yeah, or really any guessing. Okay, so a third example, f of x is x plus natural log of x. So we can guarantee that there is a root of this function f of x using intermediate value theorem, because if I plug in x equals 0.5 and x equals 0.6, that one of these is positive, one of them is negative. So there definitely is a root of this function somewhere between 0.5 and 0.6. So if I want to write f of x equals 0 in the form x equals g of x, the most obvious way to do that is x equals minus natural log of x. So I go ahead and do that with initial guess 0.55. It's halfway in between, the midpoint of this interval. Now, I won't do it here, but if I were to do this, it actually diverges. So the problem is, I wrote this equation in the form x equals g of x using a g of x that doesn't work. So here's what I can do. If I have this equation, x equals minus natural log of x, I'll take the exponential of both sides. So on the left side, I would get e to the x. And then on the right side, I'll get e to the minus natural log of x. But that would simplify to 1 over x. So in other words, I have this equation, x equals e to the minus x. So this is an alternative g of x. And if I try to fix point iteration with the same initial guess on this equation, it's actually going to converge. So how you rewrite the original equation f of x equals 0 in the form x equals g of x is absolutely crucial. You have to write it in a way that your iteration will converge. If you're not careful, it could go the wrong way. Now I haven't told you why, like, what is the difference between one case versus the other, but I promise I will shed some light on this for you. But first, any questions about these three examples and what happened with them? Weird when lights come on. What is that? Okay. So now we'll do some analysis. First, the question of existence of a fixed point. There's a theorem, the Brouwer fixed point theorem. And what that says is, if G is continuous on a closed interval AB, and if a function G informally maps AB into itself. Now what I mean by that is, if you choose X in AB, G of X is also in AB. So under these circumstances, G is continuous and it maps a given interval into itself, then G is guaranteed to have a fixed point in the interval AB. So at least we have a relatively simple condition for existence of a fixed point. And it's actually one of the assigned explorations to prove it. Don't worry, so I'm telling you up front, the proof is a short one. Look disappointed. This is a real analysis. It involves the intermediate value here. I mean, you think a theorem was that's named after someone would be like really nasty proof, but this one is
Suspicious.
you probably told it. Our himself probably told it in public. I don't know how long ago it was, but I feel so jealous of mathematicians of long ago, because all things that we have to study, they got to prove, and like so they had such a smaller amount of mathematics to build on. Like imagine getting credit for inventing Euler's method. Okay. Yeah, there's much more pressure on us. Okay, now that's existence. What about uniqueness? Okay. So let's suppose that we have the conditions for existence. So G has a fixed point. And if it satisfies what's called a Lipschitz condition. And what that means on the interval AB. So for any xy in AB, so G of x minus G of y, absolute value is bounded by some constant times the difference between x and y. And this constant L is called a Lipschitz constant. Now, so if G satisfies the conditions of the Brouwer fixed point theorem, so it has a fixed point, and satisfies this, and if the Lipschitz constant L is less than 1, then the fixed point is unique. So some terminology for you. Under these circumstances, we say that G is a contraction. Right. So if you write your equation f(x) = 0 in the form x = g of x, and if G is a contraction, there is a fixed point, it is unique, and better still, the contraction mapping theorem establishes that the fixed point iteration is guaranteed to converge to that unique fixed point for any initial guess in AB. So now we have conditions that guarantee a fixed point iteration will work. So G is continuous, G maps the interval into itself, it is a contraction, then you're good to go. Not to it. So let's revisit. Well, wait, actually, not yet. I know it should be. We're up almost in my house. Like I know something's in there somewhere. Now this condition, Lipschitz condition, that is not easy to check, but there is a simpler condition. If a function G is also known to be differentiable, Well, g of x minus g of y over x minus y by the mean value pair is equal to the derivative at some point between x and y. So if you can verify that the derivative on AB is less or equal to some constant capital L that's less than 1, then that is, so that will work as far as guaranteeing a fixed point that there is a unique fixed point and fixed point iteration will converge. So you need G to be differentiable for that to apply that condition, but it's certainly a lot easier to check.
So you only need one such value?
What?
So you only need one such value?
Um,
Like something less than or equal to that Lipskitz constant?
well, actually, ideally you want G to satisfy the condition on the interval AB.
Okay.
Yeah, so you want the derivative to be bounded. By the way, it's a very subtle point, but notice I'm requiring that the derivative, again, on the interval AB is less than or equal to some constant capital L, and that constant is less than 1. Now, you might think, wouldn't that just state the requirement that absolute value of g prime of x is less than 1 on AB? Not the same thing. It's almost the same thing. But by having it less than or equal to capital L and capital L less than 1, I'm guaranteeing separation. In other words, 1 cannot be a limit point of the derivative. So as long as there's some separation between the derivative and 1, then we guarantee convergence, fixed point iteration.
So it can be a value that's extremely close to 1.
Yeah, L could be 0.99 something. But yes, so that way the derivative is not allowed to approach, it can't get arbitrarily close to 1. Alright, now, this is the examples in light of what we just seen. So first, x equals cosine x. Alright, so g of x is cosine, we take a derivative, we get minus sine x. So on the interval from 0 to 1, g prime is less than 1 in absolute value. Actually, so the Lipschitz constant is sine of 1. And that is less than 1, so that explains why it converges. But if I look at the derivative, okay, so back to MATLAB. This example x equals cosine x. Now, the fixed point, I need to scroll back up in my diary or in my command window to find it. Okay, it's way back here. Okay. Yeah, this is a fixed point I got. So now,
X equals.
don't need to type every decimal place. We're just getting the ballpark.
Get the,
So the derivative would be minus sine of x. And let's see what we get. Well, actually, I don't care about the absolute value. So I'll take the absolute value of that. And that's what I get, 0.67, etc. So that's not great. In fact, what this means is fixed point iteration applied to x equals cosine x is even slower than bisection would be. At least with bisection, the error is getting cut in half each time. But here, the errors can be cut down by a factor of more than 2/3. So and we want the Lipschitz constant to be as small as possible. And it's going to be something between 0 and 1, but here it's closer to 1. So that explains the slow convergence that we saw. That's that example. Now, if we take a closer look at the error, So the error would be, xk minus x star. So if I look at xk plus 1 minus x star, well, xk plus 1 is equal to g of xk. And x star is equal to g of x star because it's a fixed point. But by the mean value theorem, g of xk minus g of x star is equal to the derivative at some unknown point, ck, times xk minus x star. In other words, the new error is equal to the derivative at some point times the previous error. So this is why we want g prime to be less than 1 to guarantee that the error decreases. And we don't want the derivative getting arbitrarily close to 1 because then the error won't really decrease. But in this case, at the fixed point, the error is not much less than 1. So that's why the error isn't decreasing by much from one iteration to the next. So we want this to be smaller. The smaller it is, the faster it diverges will be. Second example, x equals x squared plus 3/16. All right, so this is our g of x. So derivative is 2x. So now, if I substitute both of my known fixed points into the derivative, well, g prime of 1/4 is 1/2, so that's fine, it's less than 1. But g prime of 3/4 is greater than 1. So that's why it was not possible to get convergence. In fact, so what we can say is, another way of phrasing it is, one fourth is a stable fixed point, while 3/4 is unstable. So if a derivative at a fixed point is greater than 1 in absolute value, then the fixed point is unstable. Fixed point iteration will not converge to it, even if the initial guess is like right there. So that explains why the behavior we got with this example. And then finally, for this third example, x equals minus natural log of x. Okay, so you take the derivative of your g of x and you get minus 1 over x. But on the interval 0.5 to 0.6, you plug values from here into the derivative, you're getting something greater than 1. Now, so suppose this happens. You write your equation form x equals g of x, and you find your derivative is too large, and fixed point iteration doesn't work. So here's what you can do. And this is actually what I did do in this example, but I'm showing you what you can do in general. So you start with x equals g of x, and then you apply g inverse to both sides. So you have g inverse of x on the left side, and on the right side you have g inverse of g of x, but that's x. So x equals g of x is equivalent to x equals g inverse of x. Now we saw the inverse function last time, talking about root finding in general. So recall, the derivative of the inverse function is 1 over the derivative of the original function. So what that means is, if your original g doesn't work because the derivative is too large, take the inverse, because then you'll be taking 1 over the derivative, guaranteeing that it's less than 1. So that is how you repair a bad x equals g of x inverted. And that's what happened with this example, x equals minus natural log of x. I took the inverse function of minus natural log of x, and I got e to the minus x, and that worked. Yeah.
Okay, well, I might be just, that question might not be substantial enough, but yeah, it's just an idea.
Okay.
So what if a function is not 1-to-1?
Oh, well, yeah, I got a problem there. Well, okay, this is where the inverse function theorem comes into play, that if your derivative is non-zero at the solution, well, oh, wait a minute, though. That's derivative of f. Okay. I really thought about it in regards to g. Yeah, so, well, as long as the derivative of g is non-zero at the fixed point, then locally it has an inverse. But the inverse function theorem guarantees that. Okay. But we don't, the funny thing is though, we don't necessarily want G to have a non-zero derivative at the fixed point. Now,
As long as it's less than. As long as it's bounded.
yeah, that's what you really need for convergence, but, yeah, so yeah, it's possible that this idea, it might not be possible to apply it, unfortunately, but, yeah. Yeah, okay, because, well, I guess worst case scenario, if a derivative, is zero at the fixed point, then inverting a derivative that's infinite, and that'd be really weird. Yeah, I can imagine that happening. Okay, but this actually takes me to my next point. Oh, wait. Oh, I'm going to be in my wait. What am I doing here? Why am I always blank space? Well, sometimes I put like a new page command in here, and I'll just delete that. Okay. Okay. All right, any questions up to this point before I talk about order of convergence? I got one out here. Okay.
I have a good question.
Yes.
I was just saying I have a good question, so I'm trying to.
Oh God.
Yeah.
It's here.
Let me make things more painful for you. Okay. Now, here's an example that I'm simply proud of that I came up with myself, and it turned out to be really interesting. I didn't expect to be interesting when I came up with it. I just wanted an example, but it just turned out that way. Never mind. Okay. So I want my f of x, I want to find a root of is x minus cosine x minus 2. So I can rewrite. So I have this equal to 0. So I rewrite it in the form x equals cosine x plus 2. So cosine x plus 2 is my g of x. Now I can confirm that g of x maps this interval 1 to 3 into itself. It makes sense because cosine x is between minus 1 and 1. Therefore, cosine x plus 2 is always between 1 and 3. So it's really g of x maps anything into 1 and 3. But this tells me that g of x is guaranteed to have a fixed point between 1 and 3. So it makes sense to try the initial guess of 2. Now, okay. I can try this out in MATLAB. So x is equal to cosine x plus 2. So I'll define g, what I did before. And my initial guess will be 2. Let's see what happens.
Let me guess, x equals gx.
Yes. Okay. So I get 1.58. All right. And then I do it again, and
It's
that's
increasing,
but that's it jumped quite a
and
bit.
now it decreased again.
1.58 to 1.98, and then back to 1.59. So first start at 2, now it's over here, and then bounces 1.98 nearly 2 and then roughly 1.6.
And then it bounces back to 1.97.
Yeah, so it's bouncing back and forth, and so it's definitely not what we want. And I'll show you a picture of this from the textbook of what happens if I were to continue. Yeah, so the first few iterations, so the actual fixed point is where the solid curve, which is x cosine x plus 2, and the dashed line is y equals x. So where they cross is where the actual fixed point is. But the iterations are clustering all far away. It's bouncing back and forth. It's like a table tennis match. Very undesirable because it would eventually converge, but terribly slowly. So here's what I thought of. Like, what if we take the average of 2 iterates? And that's what I'll do. I'm going to define a new function called h of x. So h of x is going to be equal to x plus g of x over 2.
H equals.
Okay, and then I'll reset my initial guess to 2. And let's see what happens. So I'll say x is equal to h of x.
Set it to x equals.
So now it jumps to 1.79, which is roughly halfway between the iterates I was getting before. And now I go again.
And then it drops.
But only by a little bit. Notice all the iterates now are very close to one another. In fact, it's converging quite rapidly. Okay.
It converged at 1.786.
Yeah. So if we look at why was the first attempt so slow? So g prime of x, so g of x is equal to cosine x plus 2. So g prime of x is equal to minus sine x. So I'll go ahead and evaluate the derivative. That's the value. And it's very close to 1. In fact, it's minus 1. Very close to minus 1. So that explains the bouncing back and forth. So now, if I take now h of x is equal to x plus cosine x plus 2 all over 2. So h prime of x is going to be equal to 1 minus sine x all over 2. So if I do that, 1 minus sine x over 2, and I get something nice and small. So by taking the average of 2 iterates, I created a new, a new g, but really I call it h of x, whose derivative near the fixed point is quite small. So I'm basically gaining 2 correct decimal places every single iteration. I'd have full precision within 8 iterations if I continue. So, so this underscores the importance of choosing the right g. Okay, so that's what happened in this case. Yeah, but the derivative turned out to be a lot smaller.
A lot smaller. Let me see.
That's all I'm gonna do is now and turn the diary off. Okay, so we saw, so this is a bad G, and this is a good G. So, back to the notes. Okay, so this summarizes what was done. And sure enough, we see, why. Because of the derivative, how small or large the derivative is near to a fixed point. Now, in general, fixed point iteration converges linearly. So the order convergence, which I labeled R last time, is equal to 1. And the asymptotic error constant, which I labeled last time as capital C, is the absolute value of G prime at the fixed point. But now, what if this is 0? What if derivative is 0 in that case? Well, we take Taylor expansion to find out. So if I could repeat what I did last time, xk plus 1 minus x star. Well, that's the same as g of xk minus g of x star. So by Taylor expansion, I get this term involving the first derivative. And then I get plus 1/2 times the second derivative times but xk minus x star squared, and it would continue. So if g prime at the root is 0, but the second derivative is non-zero, this term would go away. So now the leading error term is this term. And notice we have xk minus x star squared. So if g prime is 0 at the fixed point, then fixed point iteration converges quadratically. So a whole lot faster. And this would be the asymptotic error constant. It's g double prime over 2. If that derivative was also 0, then it'd be 3. So how many derivatives are equal to 0 at the fixed point determines the order of convergence. And that idea is actually going to be exploited later to produce a quadratically convergent method known as Newton's method. All right. Now, so I'd like to tell you something about this modification of the previous example. Take the average of 2 iterates and obtain faster convergence. So I kind of stumbled across this by accident. About, oh, okay, this is what this example is doing, I'll try this out. Oh, wow, it works. So I wanted to take that idea a little further. It's like, well, what if I could apply this idea more broadly, where I get a fixed point iteration, but I take some linear combination of x and g of x to try to make this derivative smaller. And what I did was, what I would do is if I could estimate the derivative of my original g, then I could take a linear combination of x and g of x to make this essentially 0. And I would, so then I would have a more rapidly convergent method. And I even gave this idea a name. I called it slope canceling fixed point iteration. And I thought, oh, I've discovered something here. Maybe I could get a paper out of this. And I was actually starting to write the paper. I even performed a proof. I carried out a proof that this idea of a slope canceling fixed point iteration is super linearly convergent. And I was so excited about this. But then I realized, after looking further at my formulas, that what I did was I accidentally rediscovered the secant method, which I'm going to cover for you after Thanksgiving break. That actually be literally the last topic of the semester. I was like, dang it! So, yeah.
Or a master now.
Yeah.
You sure discovered something.
Yeah. And the thing is, about those 200 years ago, I could have gotten credit for it. Yeah. So, oh well. Yeah.
Now, could you use bisection method on that spot? So instead of taking average, using another method?
Oh. Well, I don't know what using bisection is, how slow it is, but
Yeah.
well, okay, the reason why my idea ended up replicating secant method was because I needed a straightforward way to estimate the derivative. And I did use a secant approach. And yeah, if I had some other way of estimating it, then yeah. It was fun though, until brushing teeth, but. Okay. Alright, now. So we'll look into more systematically, some ideas to try to accelerate convergence. So you're trying to solve f(x) equals 0. So you define your g of x to be x minus lambda of x, where lambda is some constant. Now, if f prime at the root is non-zero, then it's actually possible to choose lambda, so that this fixed point iteration with this g is guaranteed to converge. And it can be proven that the convergence is linear, and this is the asymptotic error constant, 1 minus lambda f prime at the fixed point. So what that would mean is, if I could choose lambda equal to 1 over f prime, I have quadratic convergence. Now, of course, we don't know this constant, so we can't just go ahead and do that. But here's what we can do. At each iteration, so here I'm choosing lambda to be a fixed constant. What I can do is I can vary the constant from iteration to iteration. Lambda k is 1 over f prime. And what happens is this lambda, this varying lambda, because xk is converging, then my variable lambda is converging to the fixed lambda that would have led to quadratic convergence. So that is one way of deriving Newton's method, and that method actually does converge quadratically. I did in my notes. Yes, in my notes. Okay. Now, the proof that it's possible to guarantee convergence of this kind of fixed point iteration by choosing the right lambda, as outlined, so it's outlined in a couple of explorations that I did not assign, for which I'm probably grateful. Yeah, right here. These problems right here that that show how it's done. Using some ideas from well, a bit of outro. So okay. But I won't go through all that here because we've been here long enough. So fixed point iteration in general might not be the fastest conversion method for any given example because it's only limited conversion. But understanding its convergence behavior and under what circumstances it can converge more rapidly leads to the design of a more rapidly convergent method, Newton's. So Newton's method is actually what I'm going to cover next time. Speaking of which, next time will not be for a while because we don't have class on Tuesday.
Wait, we don't?
No, I'm not having any of my classes meet next week. I know I'm supposed to. But I don't
Wait a
know.
minute, why not?
I don't feel like it.
Wait, what do you mean you don't feel like?
No, there's just no need. I can cover everything I need to after the break. Because also, I mean, Tuesday evening, that's right when break is starting,
Yeah.
and I don't know, just,
Yeah, we should be grateful.
yes.
I mean, if you wanna come,
Yeah, great.
No,
So class is canceled Tuesday?
Yeah, so on Tuesday the 21st, there will not be class. So our next class will be on the 28th, the Tuesday after Thanksgiving, and we'll cover Newton's method and CCAT method. So in fact, at the time this class meets, at the time this class would be on Tuesday the 21st, I'll be on the road. So, and I'll bet some of you will be too.
be in Jackson by then.
Okay, yep, I haven't been to her to go, but.
Wait a minute. If class is not meeting Tuesday, I get to go home on Tuesday.
That's right, see? Yeah, that's a good thing. Yeah, you can go home sooner than expected. Okay, so, let's shut this down.
So remind us, why did that, so remind us, why did the class canceled?
Thanksgiving.
But Thanksgiving break.
Making it longer than it's
And
actually.
then plus I can cover everything anyway.
Yeah.
Even without that class.